right, so let's pick up where we left off. So we will talk about some basic research methods in psychology, and in particular we're going to talk about the research designs. Now, there are kind of three main approaches that we'll talk about in this particular class. So we'll talk about descriptive research, correlational research, and experimental research. However, these are very basic frameworks. There are many other ways of conducting research as well. When you get into higher not grades, I guess, but in looking at more kind of complex stuff, you'll discuss quantitative and qualitative methods and other types of ways of finding information. And so, but for right now, we will talk about these three. So what's the goal behind descriptive research? Well, just kind of like the title suggests, the goal is to describe a particular subject or groups of subjects. And so descriptive research, because of this, doesn't speak to causality. It can't say that A causes B. It's only saying this is the group that I'm describing and this is what this group or this person or this construct looks like. And this makes sense because if you look at the tools for descriptive research, you'd see that none of them can really talk about causality. So one of the main tools is using something like observation, whether that's out in the world or whether that's in a laboratory type of setting. We also use things like surveys or questionnaires or interviews that directly ask people about their opinions. And again, opinions don't tell us whether A causes B, it just tells us what is. We can also talk about tests, and these are procedures that we would kind of use to study a particular kind of construct or aptitude or interest. And again, they only tell us how a person does compared to some kind of reference point. It doesn't tell us whether A causes B. And then finally, we also use things like case studies. So that's a detailed description of a particular person or situation where a certain finding was found. So this could be, for example, a clinical study or a clinical case study on a particular interesting presentation of OCD that's maybe outside of kind of the normal realm of it and how someone would have treated it. Or for example, in psychology, some of the famous case studies around a client or a patient named HM who had a very interesting form of amnesia. And so these studies help us to kind of develop kind of curiosity about a particular subject, and maybe will later lead to other research designs and ways of finding information about how often that happens. Now, if we want to have good descriptive research, we've got to make sure that our sample is representative. So that means that our group that we are selecting for study actually matches the population that we're trying to have the results generalized to. We want to make sure that if we're using tests, that they're standardized, which means that they're presented in the same way, regardless of who the examiner is. So for example, intelligence tests are standardized. So anyone who gives an intelligence test follow the a particular set of instructions and present material in a particular type of way, and that's to make sure that we're not allowing for incidental bias or or kind of creating inequality through having standards that are different between settings. We also want to make sure that if we're using tests, that we're using tests with norms that are valid. And so a norm is an established standard of performance. And again, we also want to make sure, as is going to be a big theme throughout this little chat, we want to limit bias. So one particular type of bias is something we call volunteer bias. So people who who volunteer to complete a survey may be very different from those that did not volunteer. In other words, we're missing some important voices. So we want to make sure that we are not biasing our results by saying, well, these people who volunteered, they are, this is kind of the final say on it. We have to recognize that in selection of people, we can sometimes incidentally have bias. Now, moving on from there, we have another type of research called correlational research. And correlational research looks at the strength of a relationship between two variables. And when we're talking about variables, it's important to know that variables are things that we can describe using numbers. Now, correlational research, because it's looking at a relationship between two or more variables, it also cannot speak to causality. And the reason why will become clear in just a minute. And so when we talk about correlations, we're talking about looking at measuring something on a scale that goes from -1 all the way to +1. So a correlation of -1 would mean that it's a perfect, strong negative correlation, whereas a correlation of 0 means there's no correlation between these two variables. And a correlation of 1 means that there is a complete, strong, positive correlation between both variables. Now, I'll explain in a second how we understand this number scale, but for right now, it's just helpful for you to conceptualize that we're working on a scale from -1 all the way to +1. This picture chart here is also more just helpful in terms of helping to understand that when we're talking about these relationship between variables, we're talking about variables that would have a linear relationship to each other. And so a strong positive correlation, that's the first picture, looks like a strong line that goes from the bottom of the graph upwards on a kind of a rightish kind of slant, and you can see all those little red dots. Now those red dots are kind of data points along the way. And you can see it's a strong positive correlation because all of these data plots fall on that line, basically on or very close to that line. Whereas if you look at the last picture, you can see that the data is scattered all over this graph. That means that there's no linear relationship that's apparent between these types of these variables. And so that's really just, I guess, to kind of help you on a visual level to conceptualize what a correlation actually looks like. Now, when we're talking about correlations, we talk about positive and negative correlations. So a positive correlation is that the higher variable x is, the higher variable y is. So as one variable goes up, the other variable goes up as well. So for example, the greater the number of hours a child watches TV, the greater their levels of aggression are. So as TV watching goes up, aggression goes up. Okay, so that would be a positive correlation. Well, what about a negative correlation? Well, a negative correlation would mean that the higher variable x is, the lower variable y is. That is, as one goes up, the other goes down. Let's try this out. The greater the number of hours a child watches TV, the lower their academic achievement is. So as hours of watching TV increases, academic achievement goes down. So that would be a negative correlation. Now, we're talking at the moment in correlation about just one variable to another. In statistics, there's a statistical technique called multiple regression, and that's where we look at the relationships between a bunch of different variables and a particular outcome. So in this particular case, the example here is job performance. Well, we could run a whole bunch of different correlations. So correlation between salary and job performance, job satisfaction and job performance, years employed and job performance, and then we'd have 3 sets of relationships. Or we could run one multiple regressor and where we could see whether these predictor variables, how much do they contribute to the particular outcome variable. So this is really just to kind of give you like a brief snapshot that this is kind of one tool that we use, but it's related to this idea of correlations because it is a series of correlations. It's just kind of done in a little bit of a different way, where the particular certain predictor variables can actually help us to predict how much they're responsible for a particular outcome. However, having said the responsibility and outcome, it's important to note that correlation does not equate causation. Now, what do I mean by this? Well, social media has gotten blamed a lot over the past, decade for its role in particular kind of negative behaviors. So one of the things that we've kind of found is that there is this strange correlation between high Facebook use and high levels of reported depression. So if we look at that simple relationship, we could say, okay, well, it looks like Facebook use might cause depression. But does it? We could also go ahead and say, well, what if actually depression causes high levels of Facebook use, right? We don't know which one comes first. Is it depression or the Facebook use, right? And often as humans, we look for the simplest explanation, which is not always the most accurate or nuanced explanation. So, because the reality is that we don't know whether it's Facebook use or depression that comes first. What if it's neither and it's something else? What if having no friends leads to high levels of Facebook use and high levels of depression? Right, so that's an example of the third variable problem. So the problem with correlation is just because there's a relationship between two things doesn't mean that one is causing the other or the other is causing the one. Let me give you another example. We know that the number of people who drowned by falling into a pool between the years of 1999 to 2009 also correlates at a fairly statistically significant level with the number of films that Nicolas Cage appeared in. Is Nicolas Cage, even with his bad acting, responsible for people drowning in pools? If we're probably being honest with ourselves, we'd say that no, that's probably not the case. And yet, there is a significant relationship. So a relationship of 0.66 is a pretty high statistical relationship. This is called the spurious correlation. And so it's very important to understand that sometimes it could look like two things are related, but there are likely other things that are going on behind the scenes. So it's important for us to note correlation does not equal causation. So if we want to have good correlational research, we need to make sure we've got variables that are linearly related to each other, and we cannot assume causation, just for good measure throwing it in a third time, so that you know for your exam when this question comes up what the answer is. All right, moving on. Well, our third type of research that we're going to look at is experimental research. And the goal of experimental research is to test a hypothesis through manipulating one variable in order to discover its effect on another. Now, this is the only type of research, if it is a pure experimental design, that can speak to causality. So when we're talking about experimental research, we're talking about the fact that there's an independent variable, and we're talking about the fact that there's a dependent variable. Now, the independent variable is the one that we're using, the one that we're manipulating, and then we're seeing what the effect of that manipulation is on the dependent or the outcome variable. So if we want to have good experimental research, we have to have random assignment to groups. And random assignment is important because, first of all, it is the hallmark of a true experiment. And the reason why it is that is because when we randomly assign people to groups, we're ensuring a couple things. One, we're ensuring that the groups are as similar as possible. Two, we're also kind of assuring as much as possible that any random error that can come in through our participants or through their life experiences, that's also randomly distributed. When we're selecting people for a group, we don't want to have one group where we have all people of one traits in this group and all people of another trait in a different group. We want to make sure that we have as much randomization as possible in order to truly say that the manipulation of the independent variable actually has an outcome on the dependent or the outcome variable. The other thing that we want to do if we're doing really good experimental research is we want to have a control condition. And this is a comparison group that does not receive the treatment condition, the independent variable condition. So for example, in an immunization trial or a vaccine trial, we will have people that get the vaccine and we will have people who do not get the vaccine, and we will look at the outcomes for both of these groups. So for example, if we want to say that a vaccine is working, we would expect that the people in the experimental condition who are receiving the treatment would actually fare better than those in the control condition who do not. The other thing that we want to make sure we do as much as possible is to decrease experimenter effects. So experimenter effects is another type of bias, and that is when unintended changes happen in participants' behavior due to cues that the experimenter conveys. And there are different ways that we deal with these experimenter effects. But one of the ways that we do that is in how we set up the study. So when we set up a study, we can set it up as a single blind study, and that's an experiment in which the participants don't know whether they're in the experimental or the control group, but only the researcher does. Or we could do something like a double-blind study, and that's an experiment in which neither the participants nor the research know who is assigned to the experimental and the control conditions. And so whenever we are doing a true experiment, we want to make sure that we are decreasing bias as much and we are increasing that internal validity as much as possible. And we do that through controlling as rigorously as possible any opportunities for error or bias or other things that can impact the results. We're going to move from here on to some basic statistical thinking. So when we are talking about statistics, it's important for you to know that statistics are going to be a part of your undergraduate and if you do graduate work life, because statistics play such an important role now. The role of research has increased so much over the last decade, and so statistics are going to become very, very important to you. I also want to point out to you that statistics might just save your life. There's a great video that talks about something that we call the survivorship bias. And so I'd like for you to pause this video right now, click on that link in the PowerPoint, and check out this really brief video on survivorship bias. And basically, a real face level value, survivorship bias is one of the biases that can be kind of brought about in our life and in our statistical thinking. And that's when we only pay attention to successes while we discount the failures in a specific set of phenomena. And so take a look at this video, because I think it'll be a helpful frame for you, just to let you know and just to help to kind of highlight the role that bias plays, and help us to recognize how much bias is out there, so that when we are talking about statistics and when we are talking about things, that we are looking at things as objectively as possible. Now, when we have a statistical investigation, there are several kind of important points. So first, we plan the study. And planning the study is really when we're looking at the type of research design that we're going to use. We want to make sure that the design can actually ask the questions that we're interested in. And then we want to make sure that the design can actually facilitate the statistical techniques that we're wanting to use. So can we statistically test what comes? Then we examine the data. From the data, then, we infer some information from it, and that helps us then to draw conclusions. And so the conclusion drawing is usually what occurs when we are publishing an article or when we are in some way presenting this information to be of use to the world. So this little slide here is just for fun. It's always a good time if you can get a meme of Mark Wahlberg doing something and Andy from Parks and Rec, because they're just great guys. But we're going to talk very briefly here about just some of these things of sample size and p-values. So, if you don't get the jokes right now, you will laugh in about 10 minutes, maybe. I don't know, I hope. So when we talk about statistics, we are talking very broadly right now, but we'll talk about two different types. The first type we talk about is descriptive statistics. And like its name infers, descriptive statistics are procedures that help us to describe the research data. So we organize it and we summarize the information in some kind of meaningful way. And when we're talking about descriptive statistics, we are talking about calculating group averages. So in descriptive statistics, we're looking at things like the arithmetic mean, the median, or the mode. We'll talk about those more in a little bit of a moment. And we also look at how much the data is spread from that mean. So we look at kind of these measures of central tendency and these measures of dispersion. And we'll talk briefly about these two concepts right now. One of the things that you've probably noticed now, and that the introductory chapter kind of mentioned briefly, is that there's this idea of data being normally distributed, right? So there's kind of this normal distribution or this normal curve. And so when we talk about the normal curve, what we're saying is that in the population as a whole, there are many important characteristics that are normally distributed. So that means that, that height, for example, is kind of distributed on a particular bell-shaped curve, and intelligence as well, that these things are kind of distributed across the general population in a very particular kind of way. And so what's important for you to note about this thing is that this right here would be the middle point. So this is the average, okay? So this is the middle point of this data distribution. And then over here, this is the spread of the data from one side all the way to the other. So this is our measures of central tendency are going to look at what's the middle of the data. And then our measures of dispersion look at how far is the data dispersed from the middle. So when we're talking about measures of central tendency, we're really talking about three important concepts. So we're talking about the mean. That's the value that occurs most frequently in the distribution. In very simple terms, the mean is the average, right? So that's the sum of all the observed data that we have divided by the number of observations. But there's another way to find the middle. Another way is the median, and the median is again that extent to which the scores are all tightly clustered around the middle. And the way that we find it is that it's the middlemost data observation. So if there's an odd number of observations, it's the middlemost number, whatever that number is. If there are an even amount of observation, it's the sum of the middle two divided by 2. Well, there's a third way we can also find the middle, and that's the mode. That's the value that occurs most frequently within the data distribution. And so whatever that most frequently occurring value is, we take that and we say, hey, this is the middlemost point. So there's 3 different ways to find the middle. At the same time, so we've got these ways of finding the middle, but how do we find how far the data is spread from the middle? Well, we have several different ways. So one is that we have what we call a standard deviation. And so when you begin to read some peer-reviewed articles, you're going to see this standard deviation, or SD. And this really measures how far the range of values are from the mean, from the middle. And so the way that we calculate it is a little bit involved. We take the difference between each observed value and the mean, we square the differences, add the sum of the squares, divide by n minus 1, and then take the square and then square the remainder. We also have what's called the range, and the range is the difference between the highest and the lowest observed values in the data set. And really, to calculate that, we take the highest value minus the lowest observed value. Okay, so these are some of the measures of dispersion. Very briefly, as much as we want all of our data to be normally distributed, so that would be like diagram A there, data oftentimes in real life is not, for many, many reasons. And so there are two possible kind of combinations of things that could happen. So one is what we call kind of positive skew, and that is what's happening here in diagram number B. And what that is that there's a tail to the right, and that's usually due to an outlier data on the right-hand side of the mean. Now, when I'm saying outlier, it's probably important for me to kind of just stop here. So an outlier is data that's outside of the expected observations, all right? So when I'm talking about expected observations, I'm talking about we're generally expecting that certain numbers are all going to, or our data will all kind of be within a certain ballpark. So let's say, for example, I've got a series of numbers, 3, 3, 5, 5, 7, 5, 3, and 45. Well, 45 is significantly different from the other numbers I've just told you. And so 45 would be considered an outlier within this data distribution. And so if the outlier is to the right of the mean, you can kind of see this, what we call a tail, that the distribution is not beautifully bell-shaped, but that there's this kind of long tail that goes on. Negative skew would be if there's a tail to the left due to an outlier on this side of the mean. Now, we're going to just do a brief little exercise because, hey, it's fun. So what I'd like for you to do is I'd like for you to find the mean, the median, and the mode, and the range for the following data of ages for first-year students in an economics class. So we've got our ages there for these students in this first-year class. So what I'd like for you to do is I'd like for you to calculate the mean, the median, and the mode, the range as well, and determine what the outlier is within this data set. So pause here for a minute. Complete those calculations, and then I'm going to explain in the next slide how you probably should have come to those calculations. So go ahead and pause. All right, then let's resume. So the mean, how we would calculate that is first we're going to sum all the numbers, right, and then divide by the total numbers because the mean is the average. So if we sum everything, we're going to come up with 299 divided by 14. That gives us a mean age of 21.36. So what would be the median? So the median is we've got to find the middle of the range, and if there's two numbers, then we sum and divide them, right? So if there's two middlemost numbers, and in this particular case there are, those numbers are, if we arrange everything from smallest to largest, we come to the middle and we find that 19 and 20 are the middle two numbers. So we got to add them together, divide by 2, and so that gives us a middle or a median age of 19.5. Well, we've also then got to go ahead and find the mode, but apparently I've seen things a little bit out of order here. So we're going to just pause and we'll quickly go take a look at the outlier. So the outlier would be the data that falls outside the expected observations. And in this particular case, the number that is most divergent from the rest would be 45. That's a lot higher than any of the other numbers. And it's quite outside of the general age range of first-year students in this particular economics class. But hey, it also tells you that people go back to school at any point in time in their life. So there you go. Now, the range would be the difference between the highest and the lowest number. So what is our range in this particular set? Well, our highest number is 45. Our lowest one is 17. So the range is about 28. So there's a 28-year range between the highest and the lowest age within this particular class. All right, and now we're back to the mode, which is where I was meaning to come to. So what is the most commonly occurring number? Well, in this particular set, the mode is 17. So most students who are taking this class have just graduated high school, and now they're finding themselves in a first-year economics class. All right, that was descriptive statistics. Now we're moving on to inferential statistics. So inferential statistics allow us to infer how statistically meaningful a study's results are. So the descriptive stuff is only describing the thing for us. Inferential statistics, this is telling us what is the meaning of these numbers. Now, historically, the way that we have determined meaning for statistics is through something that we call a significance test. And so when I'm talking about a significance test, what I'm talking about is as kind of an arbitrary kind of probability value that has been used in most scientific research. And it's this probability value that the probability that our results are due to random chance, all right? And so the number that we use is p is less than 0.05. So what that means is that the smaller the p-value is, the less likely the results are due to chance, whereas the larger the value, the more likely the results are due to chance. Now, I don't expect you to have a full, deep, loved appreciation for the p-value, but at this moment in time, I just want you to be able to understand it so that when you are looking at a peer-reviewed article and you see this p is less than 0.05 or p is less than 0.001, that you kind of just have a reference point for what it's meaning. So the larger the p-value, the more likely that the results are due to chance. The smaller the p-value, the less likely that these results are just due to random chance. Now, there's a new movement afoot in psychology and the other sciences which says that, do you know what, p-values, probability values, are not the most helpful way to understand what is and isn't good research. We need to look at other things like confidence intervals. So that would be, a confidence interval takes the data point plus the range of possible scores with error kind of factored into it. So it gives us a more kind of confident picture of where this actual true data value lies. And there are also more complex statistical modeling techniques, things like Bayesian statistics and other things like that. The point, though, is I'm not going to dive into those at this moment in time because, hey, this is a first-year course. Right now, I just want to orient you to the fact that we do use statistics and that there are some rules, I guess, that are helpful for us in understanding the role of statistics. But all of these things are to help us to infer whether or not this data has a meaningful way, whether we can test these things and whether there's a meaningful conclusion that we can kind of reach. Now, there's a very important word of caution that needs to come in here, isn't there? Whether your interpretation of significance is accurate depends on many, many things. First of all, it includes your sample. Is your sample representative for the purposes of generalization? Your analytic methods. Do your data support the use of the specific tests that you've used? Your study design. Can your study design actually test what you claim it can? And then finally, your hypotheses. Are they a priori or are you p-hacking? And what I mean by this is that when you're truly making and setting up an experiment, before you even begin to do your statistical analysis, you've said, this is my hypothesis. I think that this is going to happen and this is not going to happen. All right. Now, what happens sometimes is that instead of doing that, people actually spend their time coming up and kind of combing through their data after the fact and saying like, oh, well, here's a significant relationship, and then go back and construct a hypothesis and then pretend as if that was what they were testing all along. That's called p-hacking. We don't want people to do that because it's not truly testing a particular thing. Now, finding things of significance after the fact is not wrong. But it's just in the way that we set things up and the way that we present it that's important. Now I'm going to pause here for now, and we will pick up things chatting a little bit more about Carl Sagan and his stuff in just a minute. But for now, we'll pause. Thanks.